Hey class, Mr. Donaldson here, and I'm going to give you a little video lesson today on section 2.6. But before we get there, I just want to recap what we learned from section 2.5. We know that by using the linear pair postulate and the vertical angle theorem, that if you know one angle measure formed by the intersection of two lines, then you can find the other three. So let's just talk about what you learned. So in this case, we have two lines intersecting, and they form this angle that's 50 degrees. Well, by using the linear pair postulate, we know that if two angles make a linear pair, then the sum of those angle measures must be 180 degrees. So if this is 50, I know this must be 130. By using the vertical angle theorem, if this angle was 50 degrees, this angle had to have been 50. And then by using the linear pair postulate again, I knew that if this angle was 50 degrees, these two are a linear pair, they got to add to 180, so that makes this one 130. So the idea is that when two lines intersect, if I know one angle measure, I know them all. All right, and that's important for us to remember as we go into today's lesson. Okay, so today we're going to discuss different types of angle pairs that are formed when you have two lines cut by a transversal. So a line that intersects two or more other lines in a plane is called a transversal. So for instance, I've got these two lines in the plane. This line that intersects both of them, we call a transversal. And that line in every one of these pictures will be a transversal. Okay, so let's talk about the special angle pairs that are formed. Now the first is called corresponding angles. Now, if you understand what this word corresponding means, these angles are really easy to remember. Let's take a look. Suppose there's two classrooms. Classroom A has 4 seats in it, and classroom B has 4 desks in it as well. All right? All right, now I know they're not drawn perfectly, but let's assume that they're exactly the same in every way. All right, just in different places. And suppose you sit in this seat. And you're acting up, you're not paying attention, and you're being distracting to your peers. So I say, hey, listen, you know what? I need you to leave class. Will you please go next door to classroom B, and will you sit in the corresponding seat, in your corresponding seat in that classroom? Well, my hope will be that you'd walk into classroom B, and you would sit in that same seat relative to your spot in classroom A. So the idea is that corresponding just simply means in the same place relative to two different locations. Okay? So we can take that kind of understanding and relate it to angles. So treat each one of these intersections as a classroom. All right? And suppose you sat in seat 1 in this top classroom. And I said, hey, you need to get out of here. You need to go to classroom 2, and I want you to sit in your corresponding seat. Well, in classroom 1, your seat's in the top right corner, so in classroom 2, your seat would be in the top right corner. And that's how corresponding angles work. It's just different intersections along that transversal, angles in the same location relative to that intersection. So, for instance, angle 2 is in the top right corner of this intersection. It would correspond to angle 6. And by following that logic, angle 3 would correspond to angle 7, and angle 4 would be corresponding to angle 8. And those are corresponding angles. Now, before we talk about the other angles, let's just talk about in general when lines intersect. So let's say lines intersect here. First thing is that this area in here between the two lines, we call this the interior. And that should make sense, like inside, so it's like inside those two lines. And this area that's outside of those two lines, we call this area, so all of this and this, we call that the exterior, okay? So keep that in mind as we go along. So, and one other thing to discuss is alternate, what that word alternate means. So suppose that I drew a line down the middle of the classroom, and I was like, all right, I want you all to line up, alphabetically maybe, but I'd like for you to please alternate this line as you line up. So the first kid would stand here, and the next kid would be like, okay, I need to get behind them, but I need to alternate this line, so I'll stand here. Then the next kid would stand here. Next kid would stand here. Next kid would stand here. So alternate means like on the opposite side, okay? So if I'm talking about alternate interior angles, I want two angles that are on opposite sides of the transversal, but inside the two lines, all right? So an example of that would be like angle 4 and angle 5. Now you might look at this picture and be like, well, angle 4 and 3 are on alternate sides of the transversal, and they're both in the interior. But remember, we already have a special relationship with 4 and 3, and that is that they're a linear pair. So we're not going to take over that relationship. This is how alternate interior angles are. All right, so check it out. Like, for instance, another pair of alternate interior angles would be like angle 3 and angle 6. All right, now by that same logic, this should be pretty easy. Alternate exterior angles. So they're going to be on alternate sides of the transversal, but outside of those two lines, or in the exterior of those two lines. So like angle 1 and angle 8 will be alternate exterior angles, and then angle 2 and angle 7 will be alternate exterior angles. And the last thing is same side interior angles, or other books call these consecutive interior angles, I believe. But same side interior angles look like this, like angle 4 and angle 6. They're on the same side of the transversal, but they're inside the two lines, or in the interior of the two lines, or angle 3 and angle 5. All right, so these are the different angle relationships you got to be familiar with. Let's talk about what's special about them. And this focuses on when the lines are parallel. So in this example, I've got two lines, AB and CD, are parallel to one another. You can see that I've told you this in the given. You could also see that I've marked them parallel with those little arrows. And then we got line EF as a transversal. Now, what you guys will notice, hopefully, is that angle 1 and angle 5 are corresponding angles. Angle 1's in the top left of this intersection, angle 5's in the top left of this intersection. So what we want to do is we want to try to use some inductive reasoning in this geometry software here to see if we can figure out a relationship between angle 1 and angle 5. Now check it out. I can move this transversal wherever I want, and you can see that those angles are changing size as we go. But I want you to notice that if these two lines are parallel to one another, that means they have the same slope. That means they're on the same angle. And if I take this line AB and I slide it down the transversal and sit it right on top of line CD, what you'll notice is that angle 1 and angle 5 have the exact same angle measure. You'll notice that angle 2 and 6 have the exact same angle size, and so forth and so on. And so the idea is that when you have parallel lines, those corresponding angles have to be the same size because they're parallel. Now check this out. Let me show you the angle measures here for angles 1 and 5. Notice right now they are exactly the same. Angle 1 is 127.17 degrees, and angle 5 is 127.17 degrees. And you guys, that should make a lot of sense to you. If these lines are parallel, and I could slide this guy right down here on top of this line, and those angles should be exactly the same size. Now, no matter how I move this transversal, look, same angle measure. Move it over here, same angle measure. Move it here, same angle measure. No matter where I move that transversal, or how I move it, angles 1 and 5 are always the same. So by using inductive reasoning, I'm observing the data. Hey, look, angle 1 and 5, they're the same. Angle 1 and angle 5, same measure. Angle 1 and angle 5, same measure. And then I see a pattern. You know what? When lines are parallel, it appears to me that their corresponding angles are going to have the same measure. And same measure means they're congruent. So now we can make a conjecture. And that conjecture is that if two parallel lines are cut by a transversal, then I know, or I can, we're going to agree that their corresponding angles must be congruent. And you guys, we refer to this as a postulate. Okay, your textbook calls all of these things conjectures, but Ms. Butler and I like to go a little bit further to differentiate between this word postulate and theorem. Now remember, a postulate is an agreed upon idea. We can all agree, based hopefully on that sketch, you see how obvious it is, that if you have two parallel lines cut by transversal, their corresponding angles always have to be congruent to each other. Now we can use this postulate now to build and come up with these other ideas that are theorems that we could prove based on that postulate. So let's just take a quick look, and this will make a lot of sense to you. Suppose that angle 1 was 40 degrees. Well, you guys know that every single angle around this vertex you would know now based on vertical angles, 40 degrees, and linear pairs, 140 degrees. And we just agreed, or hopefully you agree, that if the lines are parallel, angle 1 and angle 2, their corresponding angles, they got to be congruent. So this would be 40 degrees. Well, check it out. Now if you know this angle at this intersection, you know all of them as well. And so the idea is, based on that understanding or that agreement that the corresponding angles would be congruent, you can see a relationship between all of these angles in this intersection and all of these angles at this intersection when the lines are parallel. So now let's just talk about the theorems that derive from this postulate. So, but let me do this in a way of, kind of an introduction to proof. In a normal year we would actually do a formal proof of this, but I can just very informally prove to you that these things must be the case. So I want you to suppose that these lines are parallel to one another, and I'm going to draw a transversal. Okay, so check it out. We just agreed that angle 1 and angle 5 are congruent. And they're congruent because if lines are parallel, the corresponding angles must be congruent. Now we also know, so angle 1 is congruent to angle 5. We also know that angle 1 will be congruent to angle 4 because of vertical angles. Now, there's this idea that we haven't discussed yet, but I'm going to talk to you about it right now. It's a property. It's called the transitive property, and it makes a lot of sense. The transitive property says that if angle 5 is congruent to angle 1, but angle 1 is congruent to angle 4, well, that means directly that angle 5 would have to be congruent to angle 4. It just allows you to skip the middleman. All right, so like if Mr. Donaldson had $50, let's say I had $50. And I know Miss Butler and I have the same amount of money. All right, we have the same amount of money. But I also know that Miss Butler has the same amount of money as Miss Speckle. She's another math teacher at Boulder High. All right, so if Donaldson and Butler have the same amount of money, and Butler and Speckle have the same amount of money, you guys would be able to deduce, well, they have the same, so she must have 50. And they have the same, so she must have 50. So if I ask you what's the relationship about Donaldson's money and Speckle's money, you guys should be able to oh, they have the same amount of money. You're just cutting out the middleman in Miss Butler. All right? So by this understanding, if 1 is congruent to 5 and 1 is congruent to 4, we can deduce that angle 4 must be congruent to angle 5. And we could prove that by using this reasoning, this logic, and angle 4 and 5 are alternate interior angles. So we're able to prove that if parallel lines are cut by a transversal, then alternate interior angles would also be congruent. All right? Same is true for alternate exterior angles. Let's go back to my previous example. All right, so this time, check it out. Let's talk about angle, I forget, what does this angle measure? Let me look. Well, I guess it doesn't really matter. Let's just call this angle 6 for this example. All right, so check it out. I know from the corresponding angles postulate that angles 1 and 5 are congruent to each other. All right, so 1's congruent to 5 because if lines are parallel, corresponding angles are congruent. And by the same logic we just used, we know that 5 and 6 are congruent because of vertical angles theorem. Well, if 1's congruent to 5 and 5's congruent to 6, I know angle 1 must be congruent to angle 6. And look, 1 and 6 are alternate exterior angles. So I know that when lines are parallel, alternate exterior angles are also congruent. And then finally, the last one we're going to prove here is about same side interior angles. So let's see their relationship, okay? So let's go back to my little diagram here, and let me just get rid of a lot of stuff. I'm going to just get rid of everything. We're going to go back to scratch. It's going to take me a second. Actually, let me just use the eraser. That seems to be a bit more efficient. Hang tight. Just get rid of all this stuff. And I'm going to show you a relationship that's true about same side interior angles. All right, and I don't think we need angle 6 for this. All right, well, totally blew that. Let's try that again. All right, well, totally blew that. Let's try it one last time. Well, you get the point. Assume that line is still there. That was a little annoying. So, check it out. We know by the linear pair postulate that angle 1 and angle 2 add to 180 degrees. So, angle 1 and angle 2, that means they're supplementary to each other. All right? And we know by the corresponding angles theorem that angle 1 and angle 5 are congruent. So, if 1 and 2 are supplementary, that means the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. And if angle 1 is congruent to angle 5, that means the measure of angle 1 is equal to the measure of angle 5. So what I can do is I can substitute. Instead of the measure of angle 1 here, I could put the measure of angle 5 in its place. And what that means is that angle 5 and angle 2, if their measures add to 180, they must be supplementary to each other. And angles 5 and 2 are same side interior angles. So I was able to very informally deduce that in this case, when parallel lines are cut by a transversal, same side interior angles are supplementary. And I'm out of time, and we'll do the examples together in the next video.